In Chapter 6, we were looking at discrete probability distributions. But what if we're looking at continuous random variables? That's going to lead us into what is called a probability density function. So this is used when we have continuous random variables. So we're not going to be able to make a list like we did in Chapter 6. Now, some of the same requirements hold true, that if we add up all of the probabilities, it'll equal 1, and that every single probability is between 0 and 1. And since we can't list it really as a table, we show these mainly as a graph or a formula. Now, the graph means that if we think about it as everything, all of these probabilities are being shown in the graph, then if I added them all up, so the area underneath will equal 1. So we're adding them all up. And the height of the graph has to be bigger than 0 and less than 1, because all the probabilities have to be between 0 and 1. Now, when we call it a normal random variable, normal curve, this is the most commonly encountered type of continuous random variable. It's going to have this beautiful bell shape. Lovely. This is called a normal curve. We call it normally distributed, normal probability distribution. So we have this normal PDF, normal probability density function. So it has to have this perfect bell shape. It's symmetric. Left and the right sides are equal. Half of it is on one side of the mean, and half of it is the other, so very symmetrical. We also have the empirical rule, that 68% is within 1 standard deviation, 95% is in 2 standard deviations, and 99.7% are within 3 standard deviations from the mean. So empirical rule does apply. And we say that the probability that a variable is less than a value would be this area underneath. So if we added up all of the probabilities up to that point, that's how we would find the probability of being less than that value. Now, when we consider a normal random variable with a mean of 0 and a standard deviation of 1, this is said to be a standard normal random variable and a standard normal distribution. We call this a z-score. And I know that that's kind of weird, but a z-score kind of is a way to standardize everything and make everything comparable. So we would take our value minus the mean divided by the standard deviation to get it into this world where the mean is 0 and standard deviation is 1. If we get everything into this z-score world, it makes it a lot easier to find our probabilities. And we can find our probabilities using a table. And this table, A2, is actually posted online. And so we're going to practice using the table, and we're going to practice using the calculator. So I want to show how to do both. So we can use the table to find probabilities of z-scores. So the table only shows the probability of z-scores. And z-scores, again, mean that we have a mean of 0 and a standard deviation of 1. It's a perfect world. Now let me grab the table so we can look at it while we're talking about this, and I didn't have it up, so wait for me. I should have paused. Took me a second. Sorry about that. So here's the table that you'll find online. It's table A2. And the z-score notice we've got Z is marked here. So the horizontal scale, we're going to be looking at the left column and the right column. And I should start with the positives here. So let's say our z-score was 0, which is our mean. So I know that's right in the middle, right? Well, the area underneath the mean, like area to the left of the mean, so 0, and this is giving me my decimal places out, is 0.50. That makes sense because the mean is right in the middle. Now, if it's 1, my z-score is a 1, I would come down here to 1, and it'd be 0.8413 to the left of 1. What if my z-score was 2.12, and I'm trying to find the probability of being less than that z is less than 2.12. What I would do is I would find 2.1, and then the second decimal place is going to be across the top. So 2.12, that'd be there. So 2.12 will be 0.983. So assume that the heights of college women have a normal distribution with a mean of 65 inches and a standard deviation of 2.7. What is the probability that a randomly selected college woman is 62 inches or shorter? This is the same thing as asking what proportion of college women are 62 inches or shorter. So the first thing we need to do is we need to find the z-score that goes with that. So what we're trying to do is find the probability that x is less than or equal to 62. What's the probability of that? So if I'm thinking about what this is finding is if I have, oh, that's horrible, and 65 is in the middle because that's my mean, and 62 is over here, 62. We're finding, if I added up all the probabilities to the left of that, all these values, the area, it's giving me the probability of being less than 62. Well, we're going to use the table, so we need to find the z-score. And we're going to use the formula from the top, and it says that we're going to do the x value minus the mean divided by the standard deviation. What this is doing is normalizing this score so we can look at it on the table. This is also a good way to compare values. So let's see. The x is 62 minus 65 divided by, what was the standard deviation? 2.7. And so I'd go to the calculator. That's going to be and I get a negative 1.11. And that makes sense if we think about the z world. So z world, this is 0, and the standard deviation is 1. So I'm counting by ones. So negative 1, negative 2, negative 3. So negative 1.1, this would be over here, to the left of the mean. Now looking at the table, negative 1.11, that's going to be on the back side. Negative 1.1, this would be 0.1335. It's a very small percent. Now, what if we wanted to find the area to the right? So if we wanted to find the probability of someone being taller than 70 inches? So here's that 65, but we're trying to find the area to the right. Well, we know the whole thing adds up to 1, right? Now the table only shows me the area to the left. So I'd have to do 1 minus the area to the left. So let's standardize that score. So the z-score would be 70 minus 65 divided by, what was my standard deviation, 2.7. So I get a z-score of 1.85. So that's positive because it's to the right of the mean. 1.8, this would be 1.80, 1.81, 2, 3, 4, 5. Now that's if we were going to the left, 0.9678. But we want to the right, so the probability of x being greater than 70 would be 1 minus, oh, I lost it already, 1.85, 1.8, 0, 1, 2, 3, 4, 5, 0.9678. 1 minus 0.9678 gives me 0.0322. Now what if I wanted to find the area between two values? Okay, so I want to find the area, or the probability of being between 60 and 68. So between, here's 65, 60, and 68. Well, what I'd have to do is find the z-score for each and find the area to the left of both. So if I found the area from here over and then found the area from here over, and I take the larger area minus the smaller area, I'd find the area in between. So let's find the z-score for each. So we'd have one z-score that's going to be 60 minus 65 divided by 2.7, and the other z-score is going to be 68 minus 65 over 2.7. And this is going to give me the probability, oh, I'm not giving myself enough room, probability of x being less than 60, and then we'll be able to find the probability of x being less than 68, and then the probability of being between them, we're just going to subtract these. So let's see, 60 minus 65 would be a negative 5 divided by 2.7. That's negative 1.85. And then that would be 3 divided by 2.7 is 1.11. Okay, negative 1.85. 0, 1, 2, 3, 4, 5. That's 0.0322. And then 1.11. 1.101. That's 0.8665. And I'm going to subtract. I'm going to take that larger one minus the smaller one. .8665 minus 0.0322, and we get 0.8343. Now, what if we wanted to find a percentile? Let's say I wanted to find what height would be in the top 10%. Okay, so let's think about where that would be. So the top 10% would be up here, right? That'd be a height really tall. Top 10%. So what would be below that? Well, that would be 0.9, right? 0.90 below. So I would like to find the z-score that goes with that. What would be the z-score? Okay, so I'm going to look at my table and try to find 0.9. 0.9. And I might get close. Let's see, 0.9032. I'm going to go with this, 0.9015. That's going to be 1.29. 1.29. So the z-score that gives me that is 1.29. So I want to find the x that matches that. So what I'm going to do is I'm going to take the mean plus that number of standard deviations away. So the mean was 65, and we're going to add 1.29 standard deviations. So 65 plus 1.29 times 2.7. And we get 68.48. So a height of 68 would be in the top 10%. Now you're thinking to yourself, there's got to be an easier way, right? We can do it in the calculator as well. So, in the calculator, this is under normal CDF. And it's always going to need a left value, a right value, the mean, and the standard deviation. So if I'm wanting the area left of a certain value, to get a left endpoint, I'm going to need to give it, like, if we're talking about the area to the left, we're talking about like negative infinity. So in the calculator's mind, negative infinity is going to be put in as negative 1 E99. That means negative 1 times 10 to the 99th power. If I was wanting to put in positive infinity, I'm going to put 1 E99. So positive 1 times 10 to the 99th power. So let's practice with this one. So if I wanted to find the probability that the z-score is greater than 2.45, I'm going to go to distribution. We're going to normal CDF, and greater than 2.45. That means the lower boundary is 2.45. The upper is going to be 1, and the E is this, you can't see it on my calculator. It's the E is right above that comma thing here. So I'm going to do second E, 99. And notice that it already put the mean as 0 and the standard deviation as 1. And the probability of that is 0.007. Greater than negative 0.45. So negative 0.45 is going to be 0.674. Now let's do a less than. Less than, the lower boundary is going to be negative infinity. So negative 1 E99, and the upper boundary is 0.39. Get 0.6517. Now these are super easy. When it's between, we actually just put the lower boundary and the upper boundary. Normal CDF. So notice how much faster those are in the calculator versus looking at the table. But if you didn't have a calculator, you could do it in the table. Oops, I should be showing what I'm doing. Now, what about when we have a different mean or standard deviation? Guess what? Yes, we don't have to leave it as a mean of 0 and a standard deviation of 1. I can change this mean and standard deviation. So you don't always have to change the z-score. Now, first off, I want to draw a picture of this because I want us to get used to what these pictures look like. So the middle would be 11, and when we're going to go out 3. 1, 2, 3. So this would be 13, 15, 17, 9, 7, 5, because the empirical rule does still hold. So you go out 3 standard deviations in each direction. If I'm less than 8, then I'm going to start with negative infinity, which is negative 1 e to the 99th power, and the upper boundary would be 8. I'm going to change the mean to be 11 and the standard deviation to be 2, and it's 0.067. Which makes sense because 8 would be here and it'd be really small. Between 10 and 12, would be 0.383. And 10 and 12 would be a very small area right here. Greater than 7. That should be a pretty big area. So 7.62, and I'd have to put positive infinity here. And it is a big area, 0.954. In the next video, we're going to look at some applications of this practice.